Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
We have Pedro Duval visiting us. He's from MIT, professor at MIT. And this year he's been very active. He has 4 papers this year. He's going to be talking about just one of them. So I'll let Pedro start.
Thank you. Why are you killing my PC? So I'll let you explain. This is work I've done with a number of colleagues in Grenoble, Nicolas Alchou, Cyril Sola, and François Sillon, and one of my grad students, Eric Chan. And it's about trying to understand why parts of the illumination might be blurry and why you might have high frequencies elsewhere. And in general, trying to study frequency content of the radiance function as light travels through space and interacts with objects. And of course, computer graphics uses notions of frequency content in lots of places. We do a lot of sampling, issues of anti-aliasing are more easily expressed in the Fourier domain. Also, usually you don't carry out the calculations themselves in the Fourier domain. We play a lot with Fourier-like bases. So this is stolen from Peter Pike's slides from some time ago. All the work on pre-computed radiance transfer uses basis functions that are the equivalent of the Fourier bases on the sphere. And also I'll argue that we also make a lot of use of knowledge about the frequency content of the radiance, although we don't necessarily write it that way. For example, if you look at irradiance caching, the observation is that indirect lighting is typically much smoother than direct lighting, so you can afford to subsample it quite a lot here on those yellow points. So translated in Fourier, it means that it's a very low frequency signal, so the Nyquist rate is much lower, and you can afford to do nice smooth reconstruction. And computer vision also uses knowledge about the frequency content quite a lot. This is recent work by Ravi Ramamurthy, where he expressed shading as a convolution, which allowed him to solve the inverse problem in a number of cases. Here we covered the lighting or the BRDF. I don't remember. That one might be just the BRDF of that object by solving half in Fourier space, half in normal space. Shape from texture is another example where people look at the anisotropy of the frequency content locally to get the orientation of a surface. Shape from focus and defocus exploit the fact that parts of the image are going to be blurry or not depending where you focus. We recently exploited that in an upcoming paper at SIGGRAPH to solve the matting problem. So from 3 video streams, we have versions of the image where everything is sharp. Here, the foreground is blurry, the background is sharp. Here, that's the opposite. The foreground is sharp, background is blurry. And from all this information, we can better extract the foreground from the background and get that nice alpha matte. And so the goal of this work, which is mostly theoretical, is to understand where all this frequency content comes from and how it's affected by various interaction of light and objects. And we put a lot of emphasis on treating both the spatial aspects and the angular aspects. So things like texture are more in the spatial domain, while reflection is more a directional effect. And we really have a framework that allows you to express both. And lots of motivations, related to the first slide I showed. We want to understand things better just for the fun of it. But also applications to rendering where, for example, if you know that a part of the scene is going to be blurry, you can afford to subsample it like irradiance caching. So we want to generalize that to things like glossy materials. I've also been wondering for some time about aspects of pre-computed radiance transfer. If you look at what people have studied, it's mostly the number of spherical harmonic coefficients that you need to represent various phenomena. For example, here this is stolen from Peter Pike. It's various approximations as you add more and more spherical harmonic basis functions, and you see that you can reconstruct the shadow of this object better and better. But the tricky thing is that here we're talking for each vertex of the mesh, how many coefficients you use, that is what's the directional bandwidth of your function. Did I not turn on that thing?
Well, no, your mic's fine. It's just the light level's too low in here, so we're going to bring the lights back up.
Okay.
Sorry about that.
No problem. Yeah, so this is kind of tricky because we're talking about the number of spherical harmonic coefficient per point in order to approximate something that varies spatially. So there's that whole weird question of, how do you relate the sampling rate in the angular domain and in the spatial domain? And I believe that also having a more unified framework to understand frequency content might have a lot of applications in inverse problems because you can better know what's the information that's left at the end of all those light interactions. So since we're trying to cast light transport in the context of Fourier analysis, there's a lot of related work, and I won't talk about most of them. I'll mention the most relevant ones. First of all, I need to emphasize that although we're going to talk about Fourier analysis of light transport, it has little to do with wave optics and Fourier optics. So people who study Fourier optics are concerned with wave phenomena, things like interference, diffraction, that happen at a very small scale, while we're interested in much larger scale interaction that are described by geometrical optics. And maybe the work that, the original work that's the closest to what we do can be seen as Paul Hegbert's study of texture mapping. So in order to analyze texture filtering and texture anti-aliasing, Paul Hegbert recasted it as a resampling problem, where you start from a given signal that's nicely uniformly sampled on the object, you warp it due to perspective transform, and then you do a resampling in this space. And because you've got this warping, it's not uniformly sampled anymore, and you might need to do some reconstruction or some pre-filtering to band limit your signal. And that's how he derived those elliptical weighted average filters that end up being like elliptical Gaussians. And what I want to emphasize here is that he did all this study using Fourier analysis to express the notion of bandwidths and what kind of filter widths you might want to have. But eventually the calculation that everybody does to do texture mapping doesn't have any Fourier coefficient or Fourier basis at all. You just use Fourier analysis to derive a criterion for the shape and size of your filter, and then you do primal space computation. And I think that the theory that I'm going to present today, I think the potential in terms of application is in this kind of space where you use the theory to understand what's happening, to express the notion of bandwidth, but in the end, your actual computation will be done in the original domain because Fourier bases are way too painful to maintain. Of course, it's also all related to the notion of light field sampling with the various papers that happened a few years ago, where people have studied, if you've got a scene and you represent it using a light field, and I assume I don't need to tell you what a light field is, you've got those nice parametrization of lines in space, you can relate the depth of the objects to the slope of these lines in the light field, which tells you something about the frequency content in your light field. And from that, you can derive some nice reconstruction filters when you compute images from light fields. So what we're going to do has a lot of similarities with this. We'll actually see equations that look a lot like what has been derived in this context. The difference with what we do is that we add a lot more phenomena because here in this work, they mostly consider diffuse objects and they don't really look at the problem of occlusion. And finally, I'm our work can also be seen as an extension of the work by Ramamurthy and Hanrahan, or Basri and Jacob, who expressed local shading as a directional convolution. And well, the informal version of it is that if you've got a BRDF that's more and more rough, you kill more and more high frequencies, your final image will be more and more blurry. More formally, these researchers showed that expressed in spherical harmonics, it's all an actual convolution, and that a lot of things are nicely expressed in this dual domain, because then it becomes a multiplication. A lot of direct and inverse problems become much easier to solve. The limitation of these works is that they only consider directional components of lighting variation. They assume that light is at infinity, and that at any point on the object for a given direction, you always get the same lighting. So this is one of the limitations that we're going to alleviate, and there are other technical differences between what they do and what we do. Okay, so what we do, again, can be seen as an extension of all these previous things, and we just track down the frequency constant of radiance in the neighborhood of a ray. So we're going to have a bundle of rays traveling through space, maybe starting from a light source here with a given frequency constant. Then maybe we hit some occluder here with the leaf. It's going to affect the frequency constant. Typically, it's going to add a lot of high frequencies, like all blockers do. Travel more, maybe some other blockers. And as you travel, you modify the frequency content as well, kind of rotate it or shear it to be more precise. Then we're going to hit the object, also express how frequency is modified, etc., etc. So really see the light sources as your input signal, and then each interaction is going to be either a filter or a transformation of the signal. And as I said, at this point, it's mostly theoretical work. We've got a small proof of concept application to show how one might use this theory.
Fredo?
Yes?
So if you're in the neighborhood of the ray, then, I mean, it seems kind of like you shouldn't really use Fourier analysis because the signal's not periodic, just a small neighborhood. So how do you get around that sort of?
Well, you don't need periodic signals to use Fourier analysis, right?
Well, you can cheat. I mean, people do it all the time, but I mean...
That's kind of the same thing for texture mapping, for anti-aliasing in general. So you'll still learn something about the frequency content that you have looking at the Fourier equations. It's the same thing when you do your convolution. Well, actually, it's not the same thing. I was about to lie to you. There are big questions of in general, we do the study in the neighborhood. I think that, the big question is how stationary are your properties, and whether the analysis that you do is meaningful in the neighborhood, and how big that neighborhood is. But periodicity is not a big deal as far as I can tell. Fourier analysis doesn't have problems with non-periodic signals. It has problems with the fact that we're limiting the domain. So there's more a question of how you might want to window that if you actually want to do measurements, absolutely. And so in practice, if you want to measure that in a scene, typically you're going to use a smooth window to analyze your signal, and you're going to lose some resolution in the frequency domain. For the kind of insight and kind of bandwidth that we're trying to derive, it's not a big deal if we don't have super fine accuracy in the frequency domain. But yeah, it is definitely an issue. I agree. And you might ask why we don't use wavelet kind of things if we want to have better localization properties. The main reason is that the convolution theorem is this really useful thing in Fourier analysis that allows you to relate a convolution with a multiplication in the other domain. So that's kind of the trade-off here. But clearly the domain of validity of the approximations is a big issue. I agree. And but if you view it from a practical standpoint, if the various equations that I'm telling you end up saying, in the end, locally, your signal is going to be extremely low frequency. There's no high frequency possible. Then you can still safely subsample in that neighborhood, even though you might have all those problems of windowing, etc. And so the four main effects that that we study and that affect frequency content or transport in free space, where the signal gets transformed. Occlusion, whereas we said usually there's a lot of high frequencies that are created. Then the BRDF, which is fairly similar to the Ramamurti or Basri case, where we typically convolve the signal with the BRDF kernel. And finally, we'll study the effect of curvature that does also weird things on the signal. And in some cases, some of these effects will be simpler to express in the original domain, and some of them will be simpler to express in the Fourier domain. Transport and curvature tend to be nice in both cases, while occlusion is much easier to express in the primal space, while the BRDF convolution is much easier to express in the Fourier domain. The nice thing with our framework is that you get the expression in the two spaces, and if your goal is to derive bandwidth information, you've got no choice. You need information in the frequency domain. That's the most direct way to get that. So let me refine a little bit our notion of local ray neighborhood. In general, we're going to follow a central ray as it travels through space and its neighborhood. And its neighborhood is going to be a 4D slice of the radiance function that for all the points on the plane orthogonal to the central ray and for all directions. So we've got 2 dimensions on the plane and 2 dimensions for the direction. And we're going to parameterize it with a spatial component and an angular component. And I'll be extremely hand-wavy about the angles. Sometimes it's going to be the tangent of the angle. Sometimes it's going to be the angle itself. But we'll just say that the tangent and the angle are the same thing. And so just simple examples to warm up. If I've got a point light source, it's purely localized in space. So it's a Dirac in space. And in the angular domain, it's a constant, which you see here. My horizontal axis is space, vertical is angle, Dirac in space, constant in angle. So in the Fourier domain, of course, you get the dual of a Dirac is a constant. Dual of a constant is a Dirac, so I get the opposite. Another light source, like an area light source, would be a box in space times a constant in angle, and so in the Fourier domain you end up with a sinc function times a Dirac. And so we're going to follow this simple scene where we start from a light source, the box light that we've just seen, travel through space, reach blockers, travel again, and reach a receiver. And we're going to track down the frequency content starting from the sinc times the Dirac all across other light interactions. So first, we've got transport in free space. So we start with our radiance at the original local light field, move by distance d. And if you look what happens for all the rays that are parallel to the central ray, well, nothing much happens. The direction is the same. The spatial component is the same. So you can just take your input signal, copy it at the same location. Now, if you look at rays that are slightly tilted, now, of course, the direction is still the same. Light travels in straight lines, but the spatial component is slightly shifted, as I show here. And of course, the bigger the angle, the more shifted, and you end up with this big shear of your signal. It's a really simple expression where the amount of shift in the angular dimension is proportional to the spatial. No, that's the opposite. The amount of spatial translation is proportional to the direction. Okay? And as everybody should know, in the Fourier domain, if you've got a shear, you also have a shear in Fourier, but along the other direction. I don't know if everybody should know that, but it took me a while to find a book that would give me the formula before I realized that it was really easy to derive it directly, but oh well. So in the primal space, we had a shear that was horizontal. In Fourier, you end up with a shear that's vertical. And this is essentially back to those results from the Lumigraph light field literature that were telling you that the slope of the patterns for a diffuse object follow lines that are 1 over the distance of the objects. And same thing in the frequency domain. And the thing to emphasize here is that some people talk about the angle of these lines, and actually the more relevant information is the slope, because the slope, it's really a shear, it's not a rotation, and the slope is what's directly related to depth in the scene. Questions about that? So clearly the transport in free space, since it's a shear, is nice in both the Fourier and the original domain. It's not too nasty. And the reason why I have a video projector here to illustrate this effect is if you look at this projector, at the projector itself, the signal about my slides is purely in the directional domain, and it's more or less a Dirac in space. And after travel, when it reaches the projector, the signal is present both in space and in angle. And now we reach occlusion. We have that bunch of blockers, and occlusion corresponds to multiplying your radiance function by a binary visibility function. Half of them get occluded. So start from my radiance before occlusion. I multiply by this binary function, and since my blockers are nice and all planar and orthogonal to my ray, I only have constant in the spatial dimension. It's all constant in angle. If I'm here, I see the blocker in all directions. So that's what it looks like in the original space. And of course, if we have a multiplication in one space, we get a convolution in the other space. So back to Fourier, we started from that sink with a slope proportional to the distance. Now the spectrum of our blockers looks like this. Since the blockers were constant over angles, we get a Dirac in the angular domain. And since we've got that repetitive box pattern, we get something that looks like a sink here. And in particular, you've got the central lobe, which is the average amount of occlusion, that's the DC component, and those two main lobes that correspond to the characteristic frequency of the blockers. So if you convolve this with this, the main effect that you see is the three replica caused by these three lobes. As you can see here, 1, 2, 3. You've got the lobes that are a little farther away here, and you recognize this sink in here. And of course, that's what we said. The spectrum is a lot messed up now. We've got a lot of additional spatial frequencies, which is not surprising from occlusion. And so occlusion, which is a multiplication in the primal, is not as nicely expressed in the Fourier domain because a convolution tends to be a more messy expression. Before I talk about BRDS, we need to do yet another step of transport to reach the receiver. So we do yet another shear, horizontal, vertical, and now you see that actually we get some kind of slope structure again, although it's wider than what we had before because of all the additional frequencies caused by the occlusion. And so finally we reach our receiver, and we need to perform local shading. So what does local shading look like? Well, for each point you can do things independently. There's no spatial interactions between the various points. It's a purely local evaluation. And you need to take the integral, for each outgoing direction, you need to take the integral of the BRDF times the incoming lighting. And so if we look at that, ray space visualization, essentially to get the value for this outgoing direction, I put my BRDF kernel here, and I just integrate against the original lighting. For another outgoing direction, if I've got a friendly BRDF like Phong, I just need to shift things. It's a nice convolution. Oops. And of course, if it's a convolution in the original domain, it's a multiplication in the Fourier domain. So our BRDF was purely local, right? There was no, it was only at a single point. So in the spatial dimension, the kernel is just a Dirac. And in the angular dimension, it was a bell-like curve or your favorite cosine exponent expression. As a result, in the Fourier domain, you've got a constant in space because of the Dirac, and you've got another bell-like curve in the angular dimension. So in fact, what you're doing is taking your input signal and clip everything that was above or below. That's essentially the same result as Ramamurti and Basri and Jacobs, that you just band limit your signal. And in the special case of diffuse integration, your kernel is actually a constant over all angles. You integrate everything, and the corresponding spectrum change is just a multiplication by a window that's just the line of spatial frequency. So after diffuse shading, you only have frequency components along the spatial line. It's not totally surprising. I'm just telling you that a diffuse object has a color that's constant, whatever the direction at which you look at it. At least the theory kind of agrees with that, so it's a good sign. And as I said, it's very similar to what Ramamurti, Hanran, Basri, and Jacobs were saying, except that here we express it in a framework that also takes into account the spatial variation. So you can see their expression is exactly what we were saying, but in the special case where you know that all your spectra are going to be constant over space, and therefore that all your signals are going to be constant over space, and that therefore the spectra are limited to a one-dimensional line. So our theory tells you that you can more or less do the same thing if you have spatial variation, still a multiplication by some horizontal window. And so one nice implication of this in the case of diffuse shading is take the case where you've got a light source, a real light source, you've got a bunch of blockers that cast some shadow on the receiver. And the only thing we're going to change here is the scale of the blockers. Average occlusion is the same, receiver, light source are the same. And you see that at the beginning, we've got shadows, but it's at a fairly low frequency. I mean, the average distance between those big shadows is fairly high. And as you increase the size of the blockers, sure, the little dots are smaller, they occur more frequently, so you've got higher frequencies. But as you increase and increase, as you scale down your blockers, eventually you've got no frequency content at all, and your illumination is all smooth on the receiver. And one way to look at it is to remember what happens at the blocker convolution side. You remember I had my blocker function that had mostly the DC and 3 lobes that were replicating the spectrum of the incoming light. So what happens when I make my blockers smaller is that I scale up this spectrum by the usual duality of scaling in the Fourier domain. So that means that as my blockers get smaller, the characteristic frequency gets higher. So those replicas here, they get pushed higher and higher because of the shear due to transport. At the location where the convolution happens, it just pushes them on the sides, but after transport, this translates to pushing to the side and up. And so they get further and further away from the spatial line. And because of diffuse shading, this effect gets completely eliminated when the blockers are becoming small. That's kind of cool. So
does this also show that when the blockers get farther from the screen, also the fuzzy thing is bigger?
Exactly. You've got the same effect with the distance, and in this case, what you're increasing is the amount of shear here. Absolutely, yeah.
I guess there's an effect that's not from geometric optics where things start imaging the light source if the holes are really, really
You mean from wave optics?
Yeah.
Yeah.
Geometric optics.
Pardon?
Imaging an eclipse through a pinhole camera.
Oh, okay. Yes, absolutely.
That's not considered.
I can get back to this. Yes. So it's related to the Soler and Cillian soft shadow technique that showed that you can express soft shadows in the diffuse case as a convolution of the image of the light source with the image of the blockers. Absolutely, that's related to this. In the paper, we discuss how they relate. It's kind of fishy because they express the effect of blockers, which is essentially occlusion, as a convolution in the original space, while we express it as a convolution in the frequency domain. And so the reason why you might have this discrepancy is that they're considering one-dimensional functions in a multidimensional space. Quickly. There's a spatial case if you start convolving functions that look like this with functions that look like this. Things are a lot simpler. And so essentially, this is the kind of situation they're restricted to while we look at more general functions. And therefore, we need to do a convolution in the Fourier domain.
No, but I was asking a different question, which
Yes.
is, isn't there an effect where if you have very fine blockers such that they form like little pinholes of non-blocking,
Yes.
they can end up like imaging the light source, which would put back frequencies onto the receiver.
So you remember that. Yes, so you mean...
I think that's not a property of geometric optics, though.
Yeah.
It is geometric optics. No, you're right. I mean, it's if you've got a light source here and a pinhole here, it's purely geometric optics that what you get on the receiver is the inverse image of your object. That's...
Yeah, I guess that's still the same
Yeah,
principle
you could
still
run the
holds.
same analysis. That's what you'd find out.
And so, so let me remember.
But you're
But
right.
in this case, your blocker becomes a Dirac, right? So therefore, it's a messy. It's yet another messy case. Your frequency constant here becomes a constant, so you still have the effect of the blockers on the spatial line. So it makes sense that you still have a lot of high frequencies. And well, again, actually, that is what I was kind of answering. Also, I didn't realize it. In fact, what's happening is that you've got the light spectrum after transport, and you end up convolving it with a constant that's horizontal. So you're copying your spectrum here everywhere. Then you're going to shear it and take a slice. So if I shear the whiteboard instead, you're going to take a slice like this. And so this is going to be the copies of your original spectrum of the light source on the spatial line. So yeah, and you're right, it's a pure geometrical optics effect.
Oh, I was wrong.
Well, in one of the instances of the sentence. Yes, absolutely. But again, here this is all special because we have a diffuse BRDF, therefore we take only the spatial line after shading, and also we've got an input signal that's just a line. If you start dealing with more general functions, there's a little more work than just taking the inverse image of your light sources. So yes, BRDF is more or less the opposite of occlusion. It's a convolution in the original space, therefore it's a multiplication in the Fourier domain. So it's nicer in the Fourier domain. Another way to look at it is that occlusion typically adds high frequencies while shading removes them, which is not a complete surprise to people who do rendering, but oh well. And so far, I've talked only about the case of a planar receiver, and in addition that had the nice property of being orthogonal to my central ray, but I'll sweep that under the rug. Now what happens if we've got curved objects? Well, now the normal at each point is rotated. And so rotating the normal is kind of equivalent to rotating the illumination around that point before doing the local shading integral. So what does that mean in terms of our ray space? Well, if we look at what happens at the central location, there's no rotation that needs to happen because the normal is the central normal, so I just copy my function. Now if I look at the point that's a little farther away, my normal has rotated a little bit, so I need to shift everything by adding a constant angle, the angle of the normal. When I move further away, I need to shift some more. Of course, you see where I'm going. it's yet another shear, but this time in the other dimension. It's a vertical one instead of being horizontal. It's not totally surprising. Transport had some effect on the spatial component, while curvature is more a directional effect. And yes, this is yet another linearization. I do a local Taylor expansion of my surface here to say that the angle of the normal is going to be proportional to the distance, the central point. And of course, as you now know, a shear in the original domain is going to be a shear in the Fourier domain along the other dimension. So now it's horizontal in the Fourier domain, and the amount of shear is going to be proportional to the curvature of the object. And so just a quick, fun, simplistic example to illustrate how those two shears, the transport and the curvature shear, might interact in a very simple scene. Let's say we have a solar oven, and we've got sunlight coming as a parallel beam of rays that gets reflected on a concave mirror and focused on a single point where you can bake whatever you want. So if we look at it in the Fourier domain, or actually equivalently in the ray space domain, incoming beam of light, they're parallel, therefore they're constant in space, but in a direction, there's only one single direction for which they're non-zero. So in terms of spectrum, that means that it's the constant in space, so the spectrum is a Dirac, and it's infinite amount of frequency in the angular domain. When we reach the concave object, we apply the curvature shear, which is horizontal since we're looking at the Fourier expression. So we're shearing that thing, now looks like this, tilted, and then we apply a transport operation to go towards the nodal point. So this transport is going to be a shear in the other dimension. So using that series of two shears, we turn a horizontal, a vertical line spectrum into a horizontal line spectrum, or rays of light that were focused purely in angle to something that focus purely in space. So that's kind of how it interacts. And that's how deforming mirrors can have almost the impression that they're changing the distance to the objects, but not quite.
So there's one more transport between 1 and 2.
So there's one more transport from here to here, but it's a vertical shear, so it doesn't affect that thing. Yeah, absolutely. So again, to conclude, curvature is another shear along the orthogonal dimension, and just like the transport, it's nice in the two domains. Couple of details I swept under the rug together with other ones. I didn't talk about the cosine term that's described in the paper. You need to multiply by the cosine term, which is a function that depends only of the angle. It's a very smooth function. So in the Fourier domain, it's a convolution with a tiny vertical kernel that blurs your spectrum a little bit, and that explains the frequency variation due to diffuse shading. And also didn't talk about the incidence angle of the central ray. You just need to do some rotation and a scaling of the spatial dimension. And, well, I guess you're all familiar with the fact that now if I change my receiver, I'm going to scale the spatial component of my input signal. And we've looked at other phenomena which are described in our paper. Texture mapping is a very easy one. Since it's a multiplication, you get a convolution. We've looked at other forms of BRDFs that are not shift rotationally invariant, and showed that you can look at things like the Fresnel term, in which case you need a multiplication plus a convolution. Since the separable approximation is a multiplication, you need to add this operation. And we've also looked at spatially varying BRDFs, which are kind of fun because the way to model them is to look at some intermediate space between the original and the Fourier space, where you've transformed half of the dimensions into the Fourier domain and you leave the other ones unchanged. I won't go too much into detail, but that was kind of fun. So far I've only described things in 2D. We claim that it extends well to 3D, essentially because we're only looking at local neighborhoods of rays. So you, in particular in the directional domain, you can arrange your computation such that all your equations are in the equator of some spherical parameterization where things behave reasonably Euclideanly. And the fun things about 3D is that some of the aspects from 2D become anisotropic. So for example, the notion of curvature is not the same along the two principal directions of a surface, so you get some anisotropic scaling. And similarly, the incidence angle, like when I was playing with the screen or with texture mapping, it's also something that's anisotropic, which is why you get those elliptical functions in Hegbert's study. So very briefly, a proof of concept application, and I really insist it's just a proof of concept. It's far from being robust at this point. In the context of Monte Carlo ray tracing. So what we want to do is compute an image with nice glossy shading, etc. But we want to subsample shading so that in blurry regions you don't end up computing that nasty integral too often. And the visibility we evaluate at every pixel. I think actually I evaluated on 4 subpixels per pixel so that you have decent anti-aliasing. But shading for these images is evaluated for only, I think, 20,000 samples, so equivalent of a 200 by 100 image, and the final image is 800 by 500, I believe. So this is the sampling pattern that we use that, puts more samples in areas of high curvatures, put more samples on the more shiny object. And the way we derived this sampling criterion was to look at those equations of the frequency content during light transport and to express the final image space frequency as how it evolves when you change the curvature of the object, the BRDF bandwidth of the object, the incidence angle, and also we have one term that looks at the effect of blockers. The way we handle blockers is actually fairly similar to Ward's irradiance caching. We look at the harmonic distance average, so the average of the inverse distance, because it relates naturally to that inverse distance shear that we had for transport. And so, yeah, this is an image computed with uniform samples. It's fairly blurry everywhere. Using our techniques, you get a lot more detail in the areas of high curvature. And again, this is an application that uses the frequency analysis of light transport but doesn't perform any calculation in Fourier space. We just have this simple formula in the end that's something like the curvature multiplied by the BRDF bandwidth divided by some cosine and some distance. And if you can evaluate that for each pixel on the screen, you get some notion of relative bandwidth.
Can you estimate of the equator distance?
So it's actually, we compute it for a small number of points and we interpolate. So that's part of where the method can be broken fairly easily. And we use the same, so this is the harmonic blocker distance. We use the same reconstruction scheme as for the final image. And actually there's some bilateral filtering involved because I like bilateral filtering. It gives you those nice sharp edges. And we take into account the depth discontinuities, things like this. But actually, for practical purposes, if you want to make this more robust and more useful, what you really need is some way to approximate the blocker frequency content in some efficient way. And I think that constructing some spatial hierarchy and estimating the blocker distribution is one way to achieve this. Okay. So in the end, we need only fairly simple mathematical operations to describe all those various phenomena. I mean, simple linear transform and multiplication convolution theorem, so it's not so bad. And we're really excited about a number of the future work issues raised by this paper. there are a lot of questions of experimental measurement / simulation to look more at this notion of spatial neighborhood and what it really means, what's the domain of validity of some of the linear approximation. And on the theory side, there are a lot more phenomena that can be expressed in this context. I think bump mapping and microfacet and things like this are one of the very challenging ones. And I just saw some bump map filtering thing that relate to this thing really directly. What's the final effect of bump maps on the frequency content of your shading expression? Of course, things like scattering can be expressed this way too. And actually, I'm curious if you can put back some of the wave optics phenomena in this same framework. And of course, various applications to graphics and vision, mostly I think in the context of computing bandwidth information, either for ray tracing to know how many samples you need in a given neighborhood of ray space, or I think for pre-computed radiance transfer to solve the issue I was talking about at the beginning, relating the spatial and the angular sampling rate that you need. And I'm also very curious about applications to vision because, as I said, a lot of techniques who do inference from images of the 3D scene, it's very useful to be able to relay, to tell in the final image how much of the original information, such as curvature, normal, etc., is actually present or has been lost due to things such as shading, transport, etc., etc. Thank you.
What about things like glass lenses? Would they act just like a curved surface?
Yeah, so refraction, I didn't have space to put that in the paper. It's another simple linear expression locally. So, and then if you start looking at curvature, you've got another shear as well. So it's mostly the shear effect that you see. And in the end, not surprisingly, it's fairly similar to the concave mirror case. Because, yeah, that's another way to do lenses, right? Concave mirrors or pieces of glass. What can I say?
So your neighborhoods you're using now, like how do you define those spatial windows, right?
I don't. So for the practical application, I just don't. I compute for every pixel in my image the curvature. I have information about the BRDF. I have my blocker thing. So for each pixel, I have a notion of density of samples that I want to have. And then I give this to my favorite blue noise sampling pattern thing, is going to put the samples where I want them.
But even like in your analysis, right? There's some, you have some differential area around some central ray, right? But that, if your distribution of your, like you have less energy as you propagate through the scene too, because things spread out more if you look at it that way, right?
Right, so you've got some nasty issues of spreading things, and you've got issues of measures, as we quickly discussed earlier. For example, if you use the light field parameterization, the measure over that space is not uniform because you've got obvious distortions as the angles increase. So in particular, if you want to carry out calculations directly in this domain, that's a huge problem. I think if all you care about is the effect of the final frequency, some notion of local bandwidth, it's not an issue. And I think to a large extent, this is really the same situation as Hegbert's texture anti-aliasing. None of the assumptions that you make locally are valid too far, but in the end, you really don't care how far you can go for some applications. It's not as true. It's probably not more important for the inverse problems, I suspect, because there, the notion of what's the window that you're going to use to compute your filters in image space might be more crucial. I wouldn't be surprised, yeah.
Do you begin to think about the subsurface scattering and what kind of how that would
I think it's essentially a spatial filtering. It's a spatial low pass. And same thing, if you look at participating media, you have a diffusion equation in 4D space where you can relate, from one local light field to the next. You've got the phase function that's going to give you your local kernel. It's like a PDE. And so that kind of thing is expressed really naturally in Fourier. That's kind of why he more or less invented those basis functions. I think scattering is fairly friendly. Bump mapping is really the pain, because you start modulating your normal, so you have a shift that varies spatially. So the effect of that on the frequency content is kind of unclear to me. I started looking at the spectrum of that, and that was pretty nasty.
This all comes back to scale too, right? What's your window? Like, you have some aggregate behavior over some window. I mean, like BRDFs are exactly that, right? It's just an abstraction of transport at a scale. So.
And that's kind of the thing I was, or I am, kind of hoping to derive. Can you get that notion of space somehow? Can you say something about the sampling rate of microfacet bumps and things like this? Yeah. Thank you.
Someone can make only a few pinholes and start imaging the light source in a way that you can get high frequencies and see. But if you got zillions of these little pinholes, I don't know.
What happens when you have the radio pinholes? What do you?
Well, if you have a lot of them, it's going to be blurry, I think. But if you only have a few, then it's not really